Any questions of any sort? Good. So we are nearly at the end of this semester. I'm sure everyone is tired of Zoom and everything, and I think fall is going to be fully in person. So I hope to meet you all in person in fall. So yeah, and I already sent an email and a Slack message. Please make sure to fill up the course evaluations. The link is in my email on Slack, and you probably received the link from UMD itself to do it. So let's do a brief recap of the key ideas of this semester. It's impossible to go through everything that we did, but my objective in doing this recap is to try to pinpoint some of the concepts that I hope you will remember many, many years from now, 10 years from now, 20 years from now, when you have probably nothing to do with StatMech, or it's been a long time since whatever you have done. So in grad school and things like that. So there are some concepts that I hope you will remember even then. So the main key idea behind StatMech is to connect microstate with macrostate. So we want to talk about possible arrangements a system can microscopically take, given what we know about that system macroscopically, and talk about the probabilities of all these given microstate. So how do we define microstate? A microstate is rigorously defined as a point in phase space. So this phase space is very high dimensional for an n particle system, which is P1, P2, P3n, R1, R2, R3n, and it's really, really high dimensional. But in this, you could have a little box. In really continuum classical mechanics, it wouldn't be a box, it would be a finite, it would be any point. We have a box because quantum mechanics matters. So uncertainty principle means that we can't really talk about things with a smaller volume than Planck's constant, h cut. So we have such a box. Once you have defining such a box means writing down the values of R and P in that box within some error margin, the error margin being Planck's constant. So such a box is denoted as nu microstate. By the way, I'm very happy to see that 12 of you showed up for this last recap because there is no final exam. I was wondering maybe everyone will disappear, but it's great. It shows that hopefully you have some, I mean, it's hard for me to really judge things in a Zoom environment, that if you really care or not, but since you showed up, it means that you do care, which is great. It's nice feeling for me. So these 6n numbers define a microstate. And a macrostate could be given by something like the total number of particles, the total volume of this system, the total energy of this system, maybe the temperature of this system, maybe the pressure of this system, maybe the chemical potential of this system. In fact, if you think about macrostate, you can think of a menu, like going to a nice restaurant and picking from the menu. In this menu, you have to pick two course meal. So course 1 and course 2. In course 1, you can pick, should I write it course 1 or course 2? No, I should not write it course 1 or course 2. It's just a simple menu where think about picking one out of either number or chemical potential. So this is your course 1. You pick either number or chemical potential. Your course 2, you pick either temperature or energy. Your course 3, you pick either volume or pressure. You can't pick number and chemical potential at the same time. You cannot specify both of them together, okay? You will have to pick one. You cannot specify temperature and energy at the same time. If you specify the temperature, it means the system is fluctuating in energy. You can talk about mean energy. You can talk about chemical potential and mean number. But otherwise, you have to pick one out of each. So you could pick something like N, V, and E. When you pick N, V, and E, that is what we called a microcanonical ensemble, and that was our first introduction to the word ensemble. Ensemble literally means the collection of microstates, all possible microstates consistent with macroscopic information, what you know about the system. And the key challenge in StatMech is to calculate the probability of a given microstate out of this collection of microstates. Okay, so a collection, let's call this collection as S. Well, that's a bad notation. Let's just call it collection, because if I use a symbol, you will confuse it with something in thermodynamics that we have used. So we have to talk about the P nu, which is in this collection of microstates. Let's say there are 1 million possible microstates. What is the probability of observing any one of these microstates given what you know about the system? And our most fundamental approximation in StatMech was that in a microcanonical ensemble, all microstates are equally likely. For all microstates in a microcanonical ensemble. What does this really mean? This really means that if it's a constant NVE system, you can't probe anything with it, right? The volume is fixed. You are not allowing it to fluctuate. The energy is fixed. You are not allowing it to fluctuate. Number is fixed. You're not allowing it to fluctuate. So number meaning mass transfer, volume meaning mechanical pressure, and energy meaning thermal pressure. It's all these three things are fixed constant. So all possible microstates that are consistent with this N, V, and E must be equally likely. So if the number of microstates in this system is omega NVE, then the probability of observing any one microstate is simply 1 over omega NVE. That's the idea. And this really is the starting point of all of StatMech. From this, we are able to think about what happens if instead of NVE, the known observables are NVT, right? Or if instead of NVE, the known observables are mu VT. Starting from this formula, we can derive everything else. So this one we call the law of equal a priori, postulate of equal a priori probabilities, which means that if you know nothing about the system, you cannot say anything. You have to assume everything is equally likely, which makes sense. We stated this as a postulate. Using classical mechanics and things, you can show this is actually true, that you can mathematically think about why this might be true. It's a bit complicated. We did not do it in this class. So this was our first postulate. This we called the equal a priori probabilities. Postulate of equal a priori probabilities. Even before doing this postulate, we talked about something else, which was the concept of ergodicity. Ergodicity said that you can prepare a system in a certain state and let it evolve as a function of time, and then calculate the properties of this system as it evolves as a function of time, which is what you do in your experimental experiments whenever you prepare a sample, right? When you do a real experiment, you don't prepare 10 to the power 23 copies of a sample, right? You just prepare one sample, you let it study. Maybe you repeat it twice or thrice, but you let it evolve as a function of time and you study everything. So ergodicity says that by doing this, what you're doing is a time average. However, a time average is the same as an ensemble average. And this was actually the first postulate we did even before equal a priori probabilities. The idea being that time averages can be hard to calculate. Ensemble averages can be easy to calculate. All we need to do is that any observable O, its time average, will be given by going to all possible microstates, looking at the probability of that microstate, and calculating the value of that observable in that microstate. For example, in microcanonical ensemble, this would become the average of an observable would become nu 1 over omega NVE O nu, and that's it. So you need to calculate omega NVE and then you're done. So this operation of calculating ensemble averages is what we kept doing through the semester. However, in order to do this, we need to figure out what is P nu. So I showed you P nu for a microcanonical ensemble. It is just a constant. The other thing that you should remember is how did we go to a NVT ensemble? In order to think about an NVT ensemble where the system can exchange energy, we thought of a system which can, actually, let's try it. So this system can exchange energy with its environment until the environment and the system come at the same temperature, and then they are still exchanging energy, but the net flux is zero. The energy going in is the same as the energy going out. Okay, it balances out. So in order to derive the probability of a given microstate in the system, we thought, well, this is clearly not a microcanonical ensemble, but let's think of a mega system where this system is embedded in the surroundings. Surroundings are often known as bath, with which it is exchanging energy, and this whole thing is isolated. So then we could say that the probability of a given microstate for the system plus bath will be equal to 1 over omega NVE, because the whole thing is thermally insulated, mechanically insulated, nothing's going on. Then we said, okay, now let's work under the regime where the energy of the full system is much more than the energy of the system. That is, the energy of the bath dominates. Then we use Taylor series on this, right? We use Taylor series to finally come up with the P nu for a canonical ensemble, which was 1 over Q e to the power minus beta E nu, and beta was equal to 1 over KBT. And Q was the all-important partition function that we introduced here for the first time. When we talked about microcanonical ensemble, some books call omega NVE as the microcanonical partition function. And so this is the canonical partition function, which is summation over nu e to the power minus beta E nu. And we did a similar thing for a system where the number can also exchange. Then we keep constant the chemical potential, which is telling you what is the rate at which the number is exchanging. But the same idea, use Taylor series. And in this case, we get P nu as 1 over Z e to the power minus beta E nu minus mu N nu. The energy in that microstate divided and the number of particles in that microstate. So derived all these probabilities. And with this, you have the machinery to go and calculate any thermodynamic average. Not just that, you can also calculate fluctuations. So a key concept I want to emphasize here is the typical connection between StatMech and thermo is almost invariably facilitated by one mathematical function, which is the log. And at this point, you shouldn't be asking me natural log or log to the base 10, doesn't matter. It's the same thing, right? It's just a constant that is different. Typically, we think about natural log. For example, S, the entropy of the system, is KB ln omega NVE. So if you can calculate the number of microstates or the microcanonical partition function, you have the entropy. And then you can manipulate the entropy, and this will be entropy as a function of NVE. This is quite important, right? So you can now manipulate this entropy as a function of, for example, if you want to get the temperature, it will be TdS partial S by partial E at constant NV, right? Did I get it dimensionally correct? I think I did. TdS, yeah. So you can get all sorts of other things out of it. You can get the chemical potential out of this by manipulating it. But the thing is, this log always shows up. And so what does this equation mean? This equation means that 1 by T is equal to partial by partial E of KB ln omega is equal to KB partial by partial E of ln omega. So this is quite important that we rarely differentiate the partition function itself. We always take its logarithm and then differentiate it. This helps us a lot, and I will mention in a moment. But notice this is a first derivative, right? So thermodynamic averages typically correspond to first derivative of log of partition function. Thermodynamic fluctuations, and this is where the power of StatMech starts to come in. In my hand, currently on my wrist, I have a heart rate monitor, which is flashing my heart rate. It's fluctuating, 42, 43, 41, whatever, it's fluctuating. If it just stayed constant at a number, that's bad, right? If it was not fluctuating, it would mean I'm dead. Something has happened, maybe, well, it should become zero at some point, but if it's not fluctuating, something is really, really wrong, right? So fluctuations are really the characteristic of life. And when I started this semester, I told you thermodynamics, what statistical mechanics is really the study of fluctuations. In this semester, we talked about time-independent fluctuations. A couple of years from now, some of you will hopefully take Chris Jardzinski's class, the advanced StatMech class, where he will tell you about time-dependent fluctuations. We did not talk about time in this class. Time was ignored. You can read, Chandler has a chapter, which we covered most of Chandler, which is quite impressive. Chandler's chapter 8, Statistical Mechanics of Non-Equilibrium Systems, talks about time-dependent phenomena, and you can go and read it if you have any questions. By the way, I will leave this Slack channel open for this class even after the semester is over. Please come and ask me questions anytime. I do it for all my classes. I'm very happy to talk with you even in the future. So thermodynamic fluctuations typically are obtained by second derivative of log of partition function. This thing is quite important. This is quite generic. And you can even talk about third moment and higher things. It's just that you have to keep differentiating again and again. So here I showed you entropy. How is it obtained from microcanonical? Similar ideas go on to other ensembles. The Helmholtz free energy is given by minus kBt ln q of nvt if you have a canonical partition function. If you have a grand canonical partition function, then you get a grand potential, which is related to pressure times volume. But always it is the log of the partition function that matters. Now, why is this very important? That brings us to the concept of a partition function itself. So if you have a system made up of two components, let's say system 1, subsystem 1, and subsystem 2. And together, this is our big system. We call it 1, 2. Let's say the partition function for Q12, it will be some function of the partition function of system 1 and the partition function of system 2. However, if these systems are independent, then Q12 will be equal to Q1 multiplied by Q2 if 1 and 2 are independent. In other words, if you think about what is Q12, Q12 is going to depend on R1, P1, the position and momentum of everything in system 1. It is also going to depend on R2 and P2, the position and momentum of everything in system 2. What I'm saying is if that 1 and 2 are independent, then this will be a function of Q1, R1, P1 multiplied by Q2, R2, P2. Why does this matter? This matters due to our wonderful logarithmic property. If you want to calculate the thermodynamic average of something in the system 1, 2, what would you do? Again, you would always start with a log. It's never that you are actually interested in the partition function. It's always log of the partition function. So you will do log Q12, and then you will see that log Q12 is log Q1 R1 P1 plus log Q2 R2 P2. And now these can be calculated independently. Furthermore, if you are interested in the properties only of system Q1, anything related to Q1 can be calculated ignoring Q2. At this point, this should be obvious to you because they are independent. That's the whole point. So you actually don't even need to calculate Q2. you can just ignore it because when Q12 is differentiated with respect to R1 P1, this term disappears. This term disappears, right? So this we used a lot when we were talking about fluids later, right? We had in fluids, when we had the partition function of any given fluid as a function of its R and P. And then we said, okay, this is going to be some momentum partition, some position partition function, let's call it QR of R, multiplied by some momentum partition function, QP of P. Why did this happen? This happened because the total energy of the system is always given by potential energy as a function of R plus kinetic energy as a function of P. So we could do this. And now when we are interested in something that depends only on positions, we don't even have to calculate this QP of P. It would always be a prefactor. So I recommend that you go and look at the notes. Many times we calculated the momentum partition function using the de Broglie wavelength and everything, but it simply didn't matter. It just factored out in the very end. And in fact, the same thing happened typically with our cheap quantum mechanical approximation, indistinguishability approximation, when we divided by n factorial. It is important for this. And you saw an example in the midterm or one of the homeworks. Sometimes it does play a role, but for a lot of thermodynamic averages, it simply does not matter. Because when you take the log of this thing, the log of this plus log of this plus log of this, and when you differentiate it, some of the things disappear. So this property of the partition function being partitioning into different properties, into different partition functions is quite important. Okay, so this is how we set up the semester. We derived the P nu for microcanonical, canonical, and grand canonical. This finished our part 1. Then we moved on to part 2, which was the application of this to non-interacting systems, right? And in part 2, we then applied all of this to non-interacting system. One of the things we spent a lot of time studying was the heat capacity behavior. We showed how in classical mechanics, the heat capacity, let's say CV versus temperature for any system would be constant. It would be equal to 3R. However, the real behavior is quite complicated. It looks something like this. At very high temperature, it does become 3R. At low temperature, it goes something like TQ. So here we talked about density of states. There was a lot of machinery that went into all of these problems. A common machinery was the G of omega, the density of states of frequency. And we showed that G of omega, Einstein was a bit lazy. He took G of omega proportional to omega minus omega Einstein. G of omega Einstein is equal to delta omega minus omega E. By the way, does anyone want to tell me if this formula is correct or did I miss something? Is this the correct formula for Einstein density of states? Your hint is here.
You need like a 3n.
Yeah. Okay. So the idea being that when you integrate G of omega d omega from 0 to infinity, it should always be 3n. The number of oscillators in the system is always 3n. So this was the Einstein model. The Debye model was a bit complicated. I forget the exact proportionality constant, but you should remember that Debye model was proportional to omega square for frequency less than a cutoff frequency, and it was 0 for frequency more than that cutoff frequency. Okay, you can put equal to here if you really care about it. So Debye got this right. Einstein got this wrong. In Einstein, the thing went down even faster than TQ. And there was a physical reason for that. The physical reason for that was that Einstein was saying that atoms can vibrate only with one frequency, which is not true because there is always a continuum of frequencies. And so this problem of looking at independent harmonic oscillators using quantum mechanics was one of the first triumphs of statistical mechanics, where we could mix statistical mechanics with a bit of quantum mechanics and really explain as to why does the heat capacity due to phonons change as TQ. So the conclusion of all this was that the heat capacity due to phonon is proportional to TQ. We also looked at something quite interesting, which was heat capacity due to electron. Anyone remembers what was this proportional to?
Omega square.
In terms of temperature.
Oh, temperature.
Temperature. It's proportional to temperature.
Temperature. So now that Meenal answered, can you tell me why did this happen, Meenal? Do you remember without looking up your notes? What was the key idea behind this? Don't worry, let me write it down. So the key idea behind this was quite simple. The idea was that we have to think about the number of electrons at the Fermi level that can get excited, right?
Yeah.
And
Now I remember. Yeah.
Remember, and we drew that Fermi function of epsilon, and we talked about that at zero temperature, the Fermi function is at the chemical potential, until the chemical potential it is 1, and then it goes to 0. And then we looked at how it changes as temperature becomes higher. And then we did the area under the right angle triangle. And basically we said that the number of electrons close to the Fermi level that can get excited is proportional to
Half
temperature.
Half kBT. Yeah.
Yeah, that idea. So if number of electrons is proportional to temperature, through a nice back of the envelope argument, we were able to show that the heat capacity of the electron must be proportional to temperature. Therefore, the net heat capacity is to a very large extent given by AT plus B2 cube. This, however, ignores electron-phonon coupling. And I want to pinpoint this because this is a problem that many of you will face in your research, irrespective of what you're doing. I'm ready to bet if you're working on organic semiconductors or if you're working on some fancy quantum material, you will face, someday you will read papers which will talk about heat capacity, and they will talk about we are ignoring that electrons and phonons are coupled with each other. This is an open problem because what does it mean to say that electrons and phonons are independent? So what did we say here? We said it's the same thing. We have basically said that the partition function of the electron and the partition function of the phonons can be multiplied to each other. More generally, we are saying that the partition function, we are saying that the partition function for any given material can be written as partition function of electrons multiplied by partition function of ions. Does anyone know what is the name for this approximation in quantum mechanics?
Born approximation.
This is the Born-Oppenheimer approximation, right? That you can treat electrons as moving much faster than ions. And it's kind of the Born-Oppenheimer approximation. There is a separation of scales. But this is not true. In most materials, this is not true. As electrons move, so this really breaks down. If you have p electrons, d electrons, f electrons in strongly correlated systems, this will break down. And you will have to worry about the other terms in the heat capacity that come from accounting for electron-phonon coupling. And that becomes hard. That's an area of open research that people work on. So we spent a lot of time on heat capacity. We also looked at black body radiation, where we derived more formula, but all of that was application. Then we moved to part 3, which we said, okay, that was all non-interacting system. But what if things start to interact? For example, what if electrons interact with ions? So we did not look at interacting systems in all generality because there is just too much to do there, but we looked at fluids. In fluids where if it was non-interacting, if a fluid was non-interacting, and fluid is quite a generic term, then we know that pressure times volume would be given by nRT. But we know the ideal gas law does break down, and in your PChem early on, you have studied equations of state that go beyond ideal gas law, such as the Virial equation of state, such as the van der Waals equation of state, and we set about to derive all of these, and we did. Here, I want you to remember the key idea was this concept of G of R. What is G of R? A better way to remember G of R is that rho multiplied by G of R is conditional probability, right? So if you want to remember one thing, you should remember this thing, that rho multiplied by G of R is the conditional probability of observing an atom or a molecule at distance R from origin if another molecule or atom is at origin. For spherically symmetric system, we derived the machinery for non-spherical systems also. So this means that if you plot G of R, it will always start with 0. Why will it start with 0? Well, you know there is one atom at origin, so the conditional probability of observing another atom at the origin is going to be 0. As you move away from it, it will go up, and it can peak at some point. In a solid, it will come down like this. It will peak again. It will come down, then it will correspond to things like that. And at very high values of R, it will go to 1, because rho multiplied by G of R must become rho at very high values of R. Therefore, G of R becomes 1. So this is very generic, that G of R goes to R as R tends to infinity. So this is for a solid. For a gas, this thing would look more diffuse. For a liquid, it would be somewhere between solid and a gas. A nice thing about G of R is it can be measured from scattering experiments. In fact, scattering experiments often don't measure G of R directly. They measure S of K, which is the Fourier transform of G of R. This is something you can measure in scattering experiment. And the reason why do we have to go to Fourier transform? Well, believe it or not, Fourier transforms, the first time you study them, they seem very odd to me. It's like, why would you do something like this? But in nature, Fourier transform is really, really fundamental. In fact, it's quite well documented that as you are listening to my sound, to my voice right now, your eardrum is actually making a Fourier transform of what I'm saying. And your brain is doing an inverse Fourier transform of this, which just shows how fundamental it is. And that makes kind of sense, right? Because your eardrum is really trying to see what are the frequencies in your voice. And it is not talking about position, but it is talking about frequency space. And then the brain then inverts this and comes up with the actual sound. So Fourier transform are in nature everywhere. In scattering, they play more role than G of R because of Bragg's law and things like that, because X-ray and things like that, it's really, yeah, so it's fundamental to look at S of K from neutron scattering and things like that, but it contains G of R. And then we spent time talking about connecting G of R with thermodynamics of a system. We showed how G of R can tell us about the average force between two atoms. It was in the last homework where most of you got it right. We talked about potential of mean force. And then one of the things we did was Zwanzig's free energy perturbation. This was quite important, where the idea was that if you have a system with interactions, let's call it a system. Let me actually be close to the notation I have here. If you have an n particle system, and you can write it as the potential energy of this n particle system as the potential energy of some reference n particle system plus whatever remains. So this is some reference, and this is some perturbation to that reference, right? This can be done for any reference, and often the use for free energy perturbation comes from picking references carefully. Then from this, we showed that this implies that the partition function of the n particle system, the true n particle system, will be related to the partition function of the reference n particle system by calculating the ensemble average of minus beta UN1, the perturbation potential energy in the reference system. So this was Zwanzig's formula. Even though it is called free energy perturbation, this formula is exact. And in one of the papers that I have given for the final exam is from Journal of Medicinal Chemistry, where this formula is basically used to design improved drugs. So for the final exam, perhaps you have already made your mind which paper you are going to read, but I really recommend spending at least 15 minutes on the other papers, or maybe a bit more. I know you're all busy, especially during exam time, but to get a sense what the other papers are. So we had this formula. Using this, we showed how the free energy, the Helmholtz free energy, depends on the Helmholtz free energy of the reference system. We derived some terms like this, where this was order beta square, and we calculated the value of W1 and W2. We also used this to derive van der Waals equation of state, and I thought that proof was quite nice. It's done in Macquarie's book. That's where I followed it from, but hopefully my notes are also sufficient. So we did that using Hart sphere system as our reference system. And you could have done it for other reference system also. The math might become complicated. You might get better answers or things like that. So this was our fluid part, classical fluid part, where we dealt with interacting systems. We introduced the machinery of how to deal with it. We talked about radial distribution functions. For a non-interacting system, the radial distribution function will always look like this, right? For a non-interacting system. It's this deviation from 1 in the G of R that really tells us about what is the interaction going on in the system. And interaction is really a sign of life. Once you can study these deviations from G of R equal to 1, you can go and talk about what is the nature of interaction inside the system. So this was our part 3, and then we moved to part 4, which was phase transitions. In part 4, our model system was the Ising model. Normally, I do a bit more in part 4, but it's a Zoom semester, and I got a sense, given homework and everything, that people were, I didn't want to, I adjust this year to year, and so this year I did not, I think there are 1 or 2 topics I did not do. Some years I do even less, some years I do even more. It like we said, it's fluctuations, right? It fluctuates year to year. But Chandler's chapter on this is quite complete. I do not go beyond that. So phase transitions, we talked about the Ising model, which had the energy of a microstate given by minus some external magnetic field, the magnetic moment of every spin, I equal to 1 to n, and then the interaction between the spins. So this is a model that you, in your qualifying exams, in chemical physics or biophysics or physics, you could easily get a problem based around this model. And people expect you to know it in all of these departments that you're coming from. You cannot say, I don't know the Ising model. It's a model that shows up so many times in your research. And in the 6th homework, it's a creative problem where I hope you can think about how does the Ising model connect to some aspect of your research. And it shows up a lot. In chemistry literature exam, you will be thinking, oh, it's got nothing to do with StatMech. And Amy Mullin and John Forkas or John Weeks or someone will suddenly ask you, oh, can you just write an Ising model for this problem? And you will be like, wait, I studied Ising model in 687. I have forgotten it. So make sure you remember this formula, because it has led to at least 1 Nobel Prize, and I have offered you some money if you solve the Ising model in 3D analytically, and if your proof is accepted by everyone. So we studied this Ising model, and here we showed that, so our main interest here was the magnetization, the average magnetization of the system as a function of temperature. And we showed the very interesting result that in 1D, the critical temperature at which the magnetization can be non-zero is actually 0. Any thermal fluctuation in 1D is sufficient to make the system disordered. Order cannot exist at any finite temperature. In 2D, the system can behave something like this. There is a critical temperature until which order can be maintained. In 3D, this critical temperature goes up further. So this was 1D, this was 2D, this was 3D. And using Pearl's droplet argument, which is also a nice proof, and I hope you go and look at it and try to keep, it's the kind of proof that you can remember through the years, through the decades. Through Pearl's droplet argument, we showed indeed that in 1D, entropy wins, and it's always possible to create domains. In 2D, there is a temperature until which you can keep the system ordered. In 3D, this temperature goes up. We then looked at mean field theory, which treated every spin, the average value of every spin to be the same. So in mean field theory, we looked at every spin interacting with an average of all other spins. That was the idea. So we started by using average of a spin is the same for all spins, and from this we proceeded and we came up with a recursive equation which allowed us to solve for the critical temperature in h is equal to 0. And we showed that mean field theory actually gets it terribly wrong in 1D, but as the dimensionality of the system increases, mean field theory becomes better and better. And finally, we looked at renormalization group theory in the last class because a lot of material, but renormalization group theory, this was work by Wilson and Kardanoff, where we had the inspiration that instead of looking at one spin at a time, average out some of the spins and reduce the dimensionality of the system and see how does the physics of the system change. And we showed that in 1D, the physics never changes. You can keep decimating spins and the physics stays the same. If you go and read the Kardanoff paper, which I have posted online, you will see that in 2D, there is a change in the physics of the system. And that change corresponds to the critical temperature. So this is a 40-minute overview of what we have done all through the semester. This is just an intro to StatMech. I'm going to point out some resources for doing things beyond this. If you like this subject, maybe you are like, oh, glad to be done with this. I hope not. If you liked it, one of the things I would like to point out is there is an advanced course on StatMech. Let me look up the number. Does anyone remember the number of the course that Chris teaches? Let me write down the number so you can keep an eye out for it in future years. It's not taught every year. One moment. I think it's CAM 703. So I shouldn't write Jarzynski because maybe I will be teaching it, you never know. So it's CAM 703, which is Intro to Non-Equilibrium Stat Physics or StatMech, which will talk about time, linear response theory, and things like that, what happens in systems where time plays a role, because we talked about fluctuations in equilibrium. We did not talk about what if you're out of equilibrium, how do you relax to equilibrium? So these are resources for future. You can take this class if you're interested. MIT OpenCourseware has lots of material on StatMech. You can go and check it out. There is a book by Zwanzig called Non-Equilibrium Statistical Mechanics. That is a good book to read. It has no homework problems, so that makes it a bit hard to comprehend whether you're really getting the material or not. I think homework problems are very important in a subject like this. So it's kind of expensive, but if maybe you can get a second-hand copy on Amazon. It's especially special because he was a professor with us in Maryland. So you can read that book. And what else can I suggest to you? There are other books in more hardcore in physics. I could write their names. These resources can be more chemistry oriented, but if you really want to go the physics way, then of course, there are books by Patria, there are books by Kardar, and it's by Setna. You can go and look up these books and talk to me about them on the Slack whenever you want. So there is a whole lot of material on StatMech that goes on and on and on. StatMech is still very lively. Discoveries are still being made, and it's I hope you picked up some important skills in this semester. And yeah, so any questions for me? No questions, Ding Chen? I'm surprised.
I think I'm good.
You're good. Okay. You can ask me questions on Slack, especially if you have advanced questions, I'm very happy to discuss on Slack. Like I said, I will be keeping the Slack channel open, and I hope to talk to you all over there. Otherwise, I hope you stay safe, and I hope you're all getting your vaccines and, making sure to be careful, especially those of you from India. I know it's really bad back home in India. Even my family, many people are affected. So please be safe. It's a very strange way to start your grad school on Zoom, not meeting anyone. But I think things will get better. We have to be optimistic. Okay, so this was the last class. Maybe I will be teaching 703 in the future, and I will get to see you there. Otherwise, I look forward to meeting you on campus sometime soon. Take care.
Thank you.
Thanks so much.
All right.
Thank you.
Thank you.
Thanks.